Partial fractions, or partial fraction decomposition as it's sometimes called, is a way to take a single fraction and break it up into smaller fractions in general. Now the idea behind this is something like if I had a fraction like 5/6, since this denominator can be written as two different fractions, as two different factors, not fractions, factors, then it's reasonable to assume that I could have gotten to this fraction by doing some number over 2 plus some other number over 3, right? Because the least common denominator would be 6, so it's reasonable to assume that I should be able to do that. So the question is, once we have a fraction, can we actually figure out how to break it apart, how it should break apart, and then can we figure out what the constants have to be to make it true? Now we're not going to do this with numbers like the 5/6, we're actually going to do this with polynomials. So if we started out with a polynomial like 1 over x squared plus x minus 6, and I wanted to break this into two pieces, the very first thing you have to be able to do is factor the denominator. If you can't factor the denominator, then partial fractions won't work. So in this case, this denominator will factor. That factors x plus 3, x minus 2. Which means it's reasonable to assume, exactly like our 5/6 a second ago, that this would be something, I'm not going to put the something up there yet, over x plus 3 plus something else over x minus 2. Now, before I just put an a and a b up here, but by doing that, that's assuming that those things are numbers. However, we have variables involved now, so how do I know that there's not x's there? Well, the rule that you're going to do, once you break apart once you factor it and break apart into the same number of fractions as you had factors in this denominator, what goes on top, the generic polynomial 1 degree less than the denominator goes on top. Okay, now what do I mean by that? Well, in this case, this is a linear denominator, right? The highest power is 1, so it's linear. The 1 degree less would just be a polynomial of degree 0. Now over here on the right, I already scribbled this out for you for time's sake, right? If it has a degree 0, well, it's just a number. If it has a degree 1, then it's linear, which means it could take the forms from ax plus b. If it's degree 2, means quadratic, that's the generic polynomial. Third degree or cubic, that's the generic, and so on and so forth. So we just put the generic polynomial of 1 degree less on top. So since this is a linear factor, 1 degree less would just be a constant, so I'm going to put an a up there. Over here, this is linear, so 1 degree less is a constant, so I'm going to put a b up there. Okay, so now we've decided how to break apart our one fraction into two pieces, but I still have these constants that I have to figure out. The way that you're always going to do it is clear the fractions. So I'm going to multiply everything by the least common denominator. Well, we know that this is the least common denominator. That's the whole idea behind this. So if I multiply both sides by this, what are we going to end up with? Well, on that side, it's just going to clear the fractions. On this side, I'm going to have x plus 3, x minus 2 times a over x plus 3, x plus 3, x minus 2 times b over x minus 2. Or that's going to be, let's see, the x plus 3's cancel, and I have a times x minus 2 plus b times x plus 3. Now, after a few attempts at this, I would say that for most of us, it would be fairly reasonable to clear the fractions to go from here to here. Now, we still got to figure out what a and b are, and this has to be true. This statement has to be true for no matter what value of x we pick. So x can actually be anything, but a and b are going to be fixed. So how are we going to do that? Well, you actually have two different methods. We we have two different methods that we're going to take a look at on how to solve this. The first one is just, I'm going to say, picking values. I misspelled that word completely. Now, there's good news and bad news when it comes to picking values. Picking values is generally by far the easiest way to figure out the numbers, but it doesn't always work, so we need the other technique as well. But here's what I mean. Since I said, let's go, I'm just moving this up here, x minus 2, bx plus 3. Since I said this has to be true for any x value, well, let's just pick some x values and make it really easy to solve for some of the letters. Here's what I mean. If we pick, let's say let x equals 2, that would make this whole piece here go away, wouldn't it? So if I plug 2 into there, I get 1 is equal to a 2 minus 2, b 2 plus 3. So of course that's no a's, I have 5 b's, so b is equal to 1/5, right? Just divide both sides by 5. Okay, so we have one of our values. We have what b is equal to. So can we figure out what a is equal to? Well, this time, let's let x equal to, well, what would get rid of the b's and keep the a's? Well, that would be -3. So if we let x equal -3, we would get 1 is equal to a -3 minus 2, -3 plus 3. Notice that'll get rid of our b's, and we have, this is -5a. Again, skipping a step because I'm at the bottom, we get -1/5. Okay, so we actually have all the values that we need. So let's see, I'm going to go back over here, which means our original fraction, 1 over x plus 3, x minus 2 is equal to -1/5 over x plus 3 plus 1/5 over x minus 2. Now, I know it's kind of weird to see a fraction in the numerator like that, but sometimes that's all we need. Now, we could rewrite that so it's not, we could multiply the top and the bottom by 5 and write this as 5 times x plus 3 and 1 over 5 x minus 2. The book may have it written like that, but for a lot of times this is all we're looking for. Now, why would we want to do this? Well, we're going to see applications in the future why this is really helpful, but imagine, we took a fraction that had a quadratic denominator and broke it into two fractions that have a linear denominator, which means it might be easier to work with. Okay, now, let's back up. That was using our first method, just picking values for x. There's another method, it's called equating coefficients. All right, so equate coefficients, we're going to start at the same spot that we started with here and just try doing this a different way. So I have 1 is equal to ax minus 2, bx plus 3. Go ahead and distribute everything out. So this is going to be 1 is equal to ax minus 2a, bx plus 3b. And then on the polynomial side, on this side over here where all your variables are, group by like powers. So here's what I mean. Here we have some stuff that has an x. If I factor out an x, I have a plus b times x. Right? And for the numbers, well, those are just numbers, so I'm just going to go -2a plus 3b. Now I'll put it in parentheses because those are just numbers because they don't have any x's. Right? I have an ax and the bx, that gives me a plus bx. And those are the numbers. Now here's what I mean by equating coefficients. I have a polynomial on the left side and on the right side and a polynomial on the left side. If you have two polynomials, let's say like ax squared plus 5x plus 2 is equal to 3x squared plus bx plus c. If we have two polynomials equal to each other, it means they have to be the same thing, which means their coefficients have to be the same. So you can kind of see whatever's in front of the x squared on this side has to be the same in front of this side. So we can see, according to this, a would have to be equal to 3, b would have to be equal to 5, and the numbers have to be the same, so c would have to be equal to 2. So we're going to do the same thing up here, it just looks a little bit more abstract. What's in front of the x on the right-hand side is a plus b. What's in front of the x on this side? Well, we don't have any x's, so that has to be 0. The number on the right-hand side is negative 2a plus 3b. What's the number on the left-hand side? A 1. Okay, so what we end up with here is a system of equations that we have to solve. So you can use any method you want to solve this system, you know, the substitution method, elimination method. I'm going to do the substitution method because it's going to be fairly quick here. So here, if I just move one to the other side, you can see that A is equal to the opposite of B. If I plug that in over here for A, right, I'm just going to, let my red pen go. Ooh, let's see. I take this now and plug it in there for the A. That's going to be 1 is equal to negative 2 times negative b plus 3b. 1 is equal to 2b plus 3b, so 1 is 5b. Dividing both sides by 5, we get b as 1/5. Back substituting over here, so a is equal to negative 1/5. Of course, notice it's the exact same two answers we have, and we could get to the same spot. Now, for those of you who are watching, you're like, well, why would I ever do that when this was much easier to do? And this was much easier to do. But this won't always work out like this, and we'll maybe see an example here in just a minute. All right, let's try another one. See if we can figure out how to break it apart. What if I had 1 over x minus 3 2x squared plus 4. Like, if I wanted to break this, let me change that to a sum factor to 3. The first thing we want to do is, if I'm going to break this up using partial fractions, I need to make sure the denominator is completely factored. In this case, well, it's completely factored. So I have 2 factors in the denominator, so I can say that that's going to be something over x minus 3 and something over 2x squared plus 3. All right, what goes on the top? Remember, it's a generic polynomial 1 degree less than what's in the bottom. Well, in this denominator, that's linear, so 1 degree less is just a constant. This is a quadratic, 1 degree less would be linear, so that would be bx plus c. All right, so let's see. Let's clear our fractions, and I'm going to kind of skip a step here. We're going to multiply everything, all 3 terms, by this denominator. And that will be 1 is equal to a times 2x squared plus 3 plus x minus 3 times bx plus c. Something like that. All right, well, we could do a little bit of picking values to maybe come up with some stuff like, if I picked x equals 3, that would get rid of all of that, and I would be able to figure out what a was equal to, so that would work. But notice there's really not a great value to pick to get rid of everything, so I can figure out like what c is. So this may be a case, and by the way, you can do a combination of these. So if you can see a quick value like here, I can find a quick value to help me figure out what a is, you can do that. But if you, let's go ahead and distribute, let's do that. Let's let x be equal to 3. If x is equal to 3, that'd be 2 times 3 squared plus 3 plus 0. So that would be what? 9 times 2 is 18, 21a. So a is 1/21. All right, pretty ugly, but there we go. Now, is that helpful? Well, it'll be a little bit helpful in a minute here when we gotta try to solve a mess. So let's see. Now, there's no other great values, like I said, to pick for x's to make stuff go away. We could probably pick 0, but that would leave c's and a's. Let's just do this. Let's go ahead and distribute everything out. So if I do that, that's going to be 2ax squared plus 3a. When I distribute there, that's going to be bx squared plus cx minus 3bx minus 3c. All right, let's start equating coefficients, or grouping by powers, I'm sorry, then we'll equate coefficients. By what's in front of the x squareds? I have a 2a over here and a b over there, so that's what's in front of the x squareds. What do I have in front of just x's? I have a c and a minus 3b in front of my x's. And as far as numbers go, I have a 3a minus 3c. All right, did I miss anything? 4, 6. All right, so there we go. All right, so let's equate. There's no x squared on this side, so what's in front of x squared on this side has to be 0. There's no x's on the left, so what's in front of the x's on this side has to also be equal to 0. And the number on this side, so we get 3a minus 3c has to be equal to 1. Okay, so we get a little bit of good news. We're quoting on good news is we actually already know what a is, so that's going to help us figure out some values here. If a is 1/21, that's going to be 2/21 plus b, so b is negative 2/21. Okay, that'll help me figure out what c is, because now I know that that goes there. So what do I have? Let's see, that's going to be c minus 3 times negative 2/21. So c plus, let's see, that'll reduce, right, to give me a 7, so 2/7. So c is negative 2/7. And let's see, well, we already know what a and c are, so we don't have to use that. So I am going to do this real quick, though. Let's make sure it works. We know a is 1/21, so that's going to be 3 times 1/21 minus 3 times c, which is negative 2/7. Does that equal to 1? Well, that's 1/7 plus 6/7 is, yeah, that's 7/7 is 1. So our numbers are right. So now we found all three numbers that we need. We have a, b, and c. So I'm going to squeeze it right here, which means 1 over x minus 3 times 2x squared plus 3 can be written as, I know it's going to be messy, just because I randomly picked numbers. This will be 1 over 21 times x minus 3 plus, what was b? Negative 2/21 x minus 2/7 all over 2x squared plus 3. All right, I know the numbers are awful. Most of the time your numbers might be a little bit nicer than this. Don't necessarily assume that they will be, but they can be. But notice we took something that had technically a cubic denominator and broke it into a linear and quadratic, which might make some of the algebra or other things in the future a little bit easier. All right, there's one more thing that we need to look at here when we're breaking these apart, and it's called repeated roots or repeated factors. So what if I had something like, I'm just going to, instead of 1 for the 4 thing, what if I had 4x over x minus 3 to the third? Well, the x minus 3 is a repeated factor in that denominator. Since it's repeated, here's what you do. It's repeated 3 times, so you start out with what's being repeated. The x minus 3 is being repeated, and write it to every power up until you get to the power it was at, right? So the x minus 3 was repeated, so I did x minus 3 squared, x minus 3 cubed. As this was the 5th, then I'd have one for x minus 3 to the 4th, x minus 3 to the 5th. Now, this is where this gets a little bit confusing. That part shouldn't be too bad. You just need each one of them all the way up. Where it gets a little bit confusing is what goes on the top. Because if you were looking at this one, you'd say, oh, that's a quadratic, right? Because the highest power is 2. That's not the way you look at repeated roots, or slightly differently, or treated slightly different. We're only looking at what's being repeated. So you only put generic polynomial 1 degree less than the factor repeated goes on top. So for each one of these, I say, okay, I'm repeating a linear term, so a constant goes on the top of all of them. Now, I'm not going to work that one out, but let's take a look at another one that might be even uglier. What if it had been a quadratic repeated? So what if this would have been, I don't know, 5x over x squared plus 3 to the 4th? That's going to be really, really, really messy. Well, you say, okay, I have a repeated factor, and it's repeated 4 times. 2, 3, 4. So on the bottom, I'm going to have this x squared plus 3, x squared plus 3 squared, x squared plus 3 cubed, and then x squared plus 3 to the 4th. Okay, what goes on top of each one of these? Well, what's being repeated? A quadratic is being repeated, so the polynomial 1 degree less goes on the top. So that'd be ax plus b, cx plus d, ex plus f, gx plus h, something like that, right? So since a quadratic was being repeated, a linear term goes on the top for each and every one of them. Now that would take you forever because you'd have to solve for, what is that, 8 different letters. A computer would be pretty helpful for that. All right, so most of this breaks down to 2 pieces that is difficult. How do you break apart the fraction, and then solving the system of equations that generally comes out of having to do it. So they do take a little bit of practice.